As you know, networking went through an evolution in the past 10 years. Software-defined networking, SDN, has emerged as a new technology in this area by separating the control plane and data planes. Most of the SDN research is focused on the control plane, the programmability of the control plane. And the first step towards opening up the data plane was OpenFlow. OpenFlow provided a unified API on top of the forwarding elements and to enable the control plane to fill the tables in the data plane. P4, which we are focusing on in this talk, is, goes one step further by enabling the programmability and enable to program the data plane. In this figure, you can see the P4 forwarding model. What you can see here, that the forwarding pipeline consists of different elements. The first element is the parser, where you identify the header instances in the packet. Then your packet goes through a match action tables, a chain of match action tables. And then your packet is stored in a buffer or queues. At the egress side, you also apply a control program consisting of a chain of match action tables. After that, your packet is egressed. The parser is described as a parser graph by the P4 program, while the control programs consisting of the tables and match action tables are described by the P4 program as well. However, the content of the table are coming from the control plane in runtime. So during the operation of the switch, you have to fill the tables and it will operate accordingly. In the next slide, you can see some examples for P4 elements. You can see how you can describe an Ethernet header consisting of 3 different fields, how you can describe a table, an LPM lookup table for IP addresses. Action is similar to a function, and you can see that it's built up of P4 primitives. A primitive could be modifying a field or adding some number to a field and so on. So you can see what is the difference between OpenFlow and P4. OpenFlow only focuses on providing a unified API on top of simple forwarding devices. However, the forwarding elements are strictly bound to existing protocols. On the other hand, P4 is protocol independent, and if we try to describe the relationship of P4 and OpenFlow, we can say that OpenFlow is one of the possible applications in P4. We started developing our P4 compiler called T4P4S, which is the translator for P4 switches, and we simply call it TAPAS, in 2015. It was half year after the first publication of P4 language. And at that time, the available tools for P4 was strictly limited. For example, the behavior model, which was available at that time as a software switching platform, was only good for validating P4 programs and analyze the behavior of P4 programs. And it was not a high-performance packet processing tool. So at that time, there was a need for developing a compiler supporting high-speed backends like DPDK, ODP, or other platforms. And we also wanted to address another target or other goal, which was namely to support multiple platforms with a single compiler. In the next slide, you can see the concept of TAPAS. You can see that we have a P4 program which describes the table descriptions, the headers, the control programs, and our compiler generates a switching program. However, the switching program consists of 2 parts, a core part which is hardware independent and a hardware dependent part which we called network hardware abstraction library. This network hardware abstraction library is currently implemented for free-scale network processing units, DPDK, and OpenWRT. Our compiler has two unique features. The first one is the easy retargetability, and the second is the high-speed packet processing. The easy retargetability was addressed by the design of TAPAS. If you have a look at this figure, you can see how the compilation architecture looks like in TAPAS. First, we have a P4 program. Then, using the high-level intermediate representation of the P4 consortium, we generate an intermediate representation of the program. And then this intermediate representation is compiled by the core compiler to a hardware-independent code. However, this hardware-independent code relies on the top of the interface of the network hardware abstraction library. In addition to the hardware-independent core program, we also need a network hardware abstraction library implemented for the given target. So it should be hardware-dependent. And at the last step, we compile or link the two parts together and generate the switch program that can run on the given platform and provide high-speed packet processing. Of course, this design has advantages and disadvantages. On the pro side, we can say that it results in a much simpler compiler design. The modularity enables us to add new features without modifying the hardware-dependent part. And of course, the core C program is independent of the network hardware abstraction library. So whenever we want to move the program and our compiler to a new hardware platform, we only have to implement a new network hardware abstraction library. On the con side, this kind of separation will result in a potential lower performance because of the lack of optimization. The key concept of TAPAS and the separation of the core and the network hardware abstraction library can be seen in this figure. What you can see here that in the core we have a representation of the packet. We can describe and implement the controls, including ingress and egress control. We can apply tables and do key calculations. And of course, we can implement the actions. However, the packet representation, the packet descriptor, is coming from the network hardware abstraction library, since the packet representation should be different in the different architectures. For example, in DPDK, RTMBuf is used to represent the packets. However, in other platforms, maybe a different structure is used. Of course, the table configuration and counter configuration is also part of the network hardware abstraction library, because it's different in different architectures. Okay, furthermore, lookup table instances and primitive actions or functions are also described by the network hardware abstraction library. And what you can see that if we implement an action, we will use the primitives of the network hardware abstraction library. We started developing TAPAS as a university project, and as you know, in a university project it's always a problem to generate a software product which is mature enough. And this is also a program with TAPAS that we have to take care of the incoming request and so on, and we don't have a support team for this. In addition, we also have several research questions we have to solve. For example, currently TAPAS applies a run-to-completion model, which means that the packet is first received, and after that a single CPU core is assigned to process the packet from the beginning to the end. However, there are other models as well. So, for example, we can split the pipeline into different parts and assign the different parts to different cores. And in this way, for example, we can do pipeline scheduling. So some parts of the pipeline may be more important than the other parts, and in this way we can assign more resources to the important part and less resources to the less important parts. Another research question is how to support hardware accelerators, because lots of hardware platforms carries hardware accelerating functions, and these functions can be called in an asynchronous way. However, if we have a P4 program, it means that at a point of the P4 program we have to stop and suspend the execution of the packet processing, then wait for the hardware accelerator to finish its job, and after that we have to continue the pipeline from that point, and it's a still big challenge how to solve it in a fast way. Finally, traffic management is required by lots of network applications. However, traffic management is not part of P4 at the moment, and the work on extending P4 by traffic management has started recently. Our team is also taking part in this work, and we hope that we can add the achievements of this working group to TAPAS as well. TAPAS is an open source P4 compiler supporting high-speed backends like DPDK, ODP or native Linux. If you want to try it or if you want to contribute to our project, just go to our GitHub.